Okay, so today we're going to start chapter 4. We're going to cover chapter 4 all week. And chapter 4, we're looking at linear relationships. And correlation. All right, so this is for what we call bivariate data. Bivariate data, we're looking at numerical data in two variables. So we have our X and our Y variables. X is what we call the explanatory variable, and Y is what we call the response well, we'll just call it the response for now. Sometimes I'll share with you some other names for different things, and I'll throw that in there. Okay, so an example of bivariate data could be something like height and weight. And what we would look at for like height and weight is we want to know, does the explanatory variable X, so does X explain or predict Y? So does someone's height explain or predict someone's weight? That kind of thing. So that's what we're looking at. The explanatory variable explains or predicts the response, the Y. So this is one thing we will learn is how to read a problem and know which one is my X variable and which one's going to be my Y variable, because it matters. So which one's the explanatory and which one's the response. So when you read through a problem, if it's not given to you, then you'll have to read through and say, okay, well, which variable would explain or predict the other? And sometimes it can kind of go two different ways. And in those situations, it'd be given to you. But don't get caught up with the fact that you might have to figure one out over another. So I want to talk to you about with these two variables that we have a visual, we have a graph we can look at. And what we do when we talk about, and when we see this visual, what do we talk about? How do we describe it? That kind of thing. So we'll start with that, with these two variables. So a graph of this linear relationship is called a scatter plot. And we can draw this very easily out by hand, but if we have a lot of data, it's not so easy. But we can have our technology do it for us. So when we have a scatter plot, each XY pair is a dot or a point on the graph. So let me show you what I mean. So we might be looking at all these dots. It might be kind of like this. Okay, so you can see those. This would be like a scatter plot. I'm gonna make them a little darker so you guys can see them. Okay, there we go. Scatter plot might have one down here, could have one over here, right? And what I want you to notice is this is a scatter plot, and when we look at this, we're kind of looking to see, well, what is this telling us? So we need to know, what does our X represent and what is our Y representing in specific for a problem in the context. So if we took a look at the example that I just gave you with height and weight, I could say, okay, well, height down here is my X, right? That's my explanatory variable. And then over here, I have weight, which is the Y, which is my response, or we call it predictor. It's what's predicted. Okay, variable here. I feel like this is kind of not clear. I apologize. That might be better, maybe not. Okay, so I have this, and this is what we're looking at. So what we're looking at is as height increases, right? What's happening to y? So this kind of follows right along with algebra and stuff that we've learned in high school. So as x is increasing, what's happening with my y? Well, it looks like my y is also increasing, doesn't it? It looks like I have a positive slope to a line right there. And that's really what we're looking at here. I mean, I do have a couple odd values, which I would consider those unusual values. These would be my outliers, right? But everything else basically follows this line right here on my pen. So I would say as x increases, y also increases. But of course, when I say something like that, I want it in context. I want it specific. So we're going to describe, just like we would a distribution, we're going to describe the relationship in the graph. So we want to describe that relationship between x and y that we see in the graph. So the first thing we're going to say, just like I said, as x increases, what happens to my y? Then y does what? It will either increase or decrease, assuming it's linear. So that's one thing we can state about the graph. Another thing is we want to ask ourselves the question, do we see a pattern? So it's not always linear, but it could be. So if we see a pattern, we could say maybe we see something linear or curved, right? It could be quadratic specifically. And we want to mention something like that when we're looking. This is all visual, right? No calculations, just all visual. And of course, do we see any outliers, right? So we always want to throw in those outliers or unusual values. And remember, that's because if I have outliers, it kind of changes maybe how I'm going to calculate things and view the distribution, right? Because those outliers are going to skew some numbers. They're going to kind of change what they would be if we didn't have those outliers. So if we didn't have these two values right here, if those were gone, then everything would be in a really good straight line there. But since those are there, it's going to skew some measurements that we get from this graph. So when we're describing a scatter plot, this is what we're going to look at. What happens to y as x increases? And do we see a pattern? Do we see any outliers? So it's very simple, nothing too detailed. And of course, when we talk about things like this, we always talk in context. So let me just always write that. We always want to write complete sentences in context. So we want to write about the problem specifically, right? So if we're looking at the height and the weight, then we want to say, okay, as height increases, weight appears to also increase. All right. When we're looking at this visual, at this scatter plot, we have some calculations that can go along with this. So we're going to talk about this calculation and a number that goes along with this, and that's my correlation value, and see what that means and what those numbers represent and how it can also talk about that relationship between x and y. So this is called the linear correlation value. Now, I want you to understand that I call it a value And some books may call it a coefficient. It may be called linear correlation coefficient. The only reason why I call it a value is because next class we have another coefficient and I just try to keep them separate. Okay, I try to make it a little bit easier in that way, but just know it could be called a linear correlation coefficient. And what this does, this measures, so it's a measure of strength of a linear relationship between X and Y. So what's so important right here is this word linear relationship. This is so important. Now, the reason why that's important is because this value only measures a linear relationship strength between X and Y. So if we notice when we look at the plot, if we noticed a quadratic relationship, it might be a strong relationship, but my linear relationship wouldn't be strong, right? Because it's quadratic, it's curved. So in that case, I wouldn't get a good number here. So I just want you to know this is to represent just that linear relationship. So just a relationship that's a straight line. So I'm going to give you some notation. So the first one is called rho. Of course, this is a Greek letter, rho, and this is going to stand for the population correlation. But we don't really use rho because we're not really studying a population, right? We're usually studying a sample, and that is just R. So R, lowercase r, is my sample correlation value. And this is the one we're going to use. I like to give you the notation and everything about even the population in case that comes up. But you know, here in our class, we're studying samples almost all of the time, except for one chapter, which we'll get to that later on. So I want to give you the scale of this R value. So R can go between -1 and +1. So R is a value between -1 and +1. So if -1 is all the way down here and then +1 is up here, then 0 would be right in the middle of our scale. And I'm going to give you an idea of what words we associate with these numbers. Okay. And I'm actually going to break it up 0.4 and 0.8 and -0.4 and -0.8. Okay. So with this, we consider an R value that is between -1 and -0.8 to be strong. So we have a strong linear relationship between X and Y. And the same thing on the positive side. Between 0.8 and +1, we have a strong linear relationship between X and Y. Between -0.8 and -0.4, we consider this a moderate strength relationship. And same thing between 0.4 and +0.8, moderate. So you can see how it's symmetric here. It's a mirror image if you fold it on 0. And then right in the middle between -4 and -0.4 and +0.4 here, this is what we would consider a weak correlation. We would say that it's a weak relationship between the two variables X and Y. So this is taking a calculation and getting this number R here. We'll get one single number, and we're going to take this calculation, and then we can put words to that number, into that calculation, and explain what this relationship what strength it actually has in this graph based on this one number by using these. Okay. If I have a linear correlation of 0, so here, meaning if R is equal to 0, this means there is no linear correlation. So what that means is that I might have a correlation, it's just not a straight line. So I might have a relationship between X and Y, it just wouldn't be a straight line. Okay, so if we see a correlation that's -1 or a +1, these are what we call perfect linear correlation or relationship. And what that means, is if I'm on a graph, it would be a complete straight line. It would mean that all of my points just line up perfectly in a straight line. I could just connect it with a pen, like drawing a line. Okay, that's what that would mean. R is affected by outliers. Here it is. This is why we need to mention if we have outliers or not. R is affected, it's sensitive to outliers, meaning when I have outliers on my graph and I have outliers in my data set, this R value will change. What that means is maybe I have a fairly strong linear relationship between height and weight, right? A 0.8 maybe. But when I have those outliers, maybe the outliers are actually bringing it down. So it's more of a moderate strength relationship. Maybe it's a 0.6, but if I took those outliers out, maybe it's a 0.8. So if you have outliers, they're going to bring your linear correlation closer to 0, right? It will weaken that number, bringing it closer to 0. It's going to make it appear like the relationship is weaker than it actually is if you didn't have those unusual values. So we like to mention that we have those. I'm going to also give you the calculation for R, and I want to assure you we will never do this by hand. I'm going to give it to you. I'm going to squeeze it in here. I don't really even have enough space for it right here, but I'm just going to squeeze it in right here. You don't have to write it down if you don't want to. It will be on the notes, right? The notes are out there for everyone to have all the time. And it is a long calculation, and that's why I will never do this by hand. But I just want you to know what it is. And really even seeing this one, it doesn't really make a ton of sense for us, but at least I'll just give it to you. This is my R value calculation. So it's a long calculation. Let me just give you a little points for, like a key for what all of these mean. So remember Xi and Yi, those are my data values. I'm just going to fill them in here. I can zoom in if we need to. Those are equal to my data values. X bar and Y bar, those are the sample means. It's just I have a mean for my X's and I have a mean for my Y. And then same thing for SX and SY. Those are my sample standard deviations. And then N, of course, is the number in my sample. My sample size. Nothing changes there. Okay. But I want you to know this is the calculation we do when we're looking at R. It can only be done on numerical data. So that's right in the beginning, I said this is for numerical data when we have two variables that we're studying. It's never just for one, and it's never on that categorical data. Okay. So I'm just going to look at a couple examples real quick of what we're looking at. Nothing really too detailed or specific. But we're always going to use our technology to get that R value for us. We're not going to do that by hand, not even on a team assignment. So for our first example, what if we have a graph that looks something like this? You guys see all that? Of course you can, because I have it zoomed in really good. So I have my X, which is my explanatory variable, and then I have my Y, which is the response variable over here. And if I wanted to describe just the visual of this, right? I don't really have a way of saying as X increases, and I would say as X increases, Y is all over the place, right? Because it's a curve. You could see this curve right here, right? It's not a straight line. So it's not so easy to describe this relationship. But I would say, okay, I do see a curved relationship. It does look fairly strong, right? I don't have like little points all over the place outside. So I would actually say it's looks like a fairly strong curved relationship with no outliers. Now, if I thought maybe there'd be an outlier, might be a value here, right? Something a little different, maybe something here or up here. You could have different outliers, and you could just see where those are, right? They're not in line with all the others. They're just kind of out there. In this case, I would say, well, it still looks like a fairly strong curved relationship, but I do have a few outliers in there. And that's how we would describe this, this graph, this scatter plot. Now here, so we could call this a non-linear relationship. And what would happen is my R value would come down to almost 0, because remember, R only represents a linear relationship. Now, if I had another example, I could have something where I have my X, my explanatory variable, and Y, the response variable here. Maybe I have something like this. Okay, you could see that's fairly strong. It's definitely linear, right? I could lay my pen over the top and almost cover all of them, right? So this, I would say it's a linear relationship, and I would talk about how strong it appears. So here I would say as X increases, what's happening? As X increases, what happens with Y? Y decreases, okay? So as X increases, I don't have any context, which I would normally. It looks like Y decreases. It looks fairly strong. Looks like a linear relationship. And at this point, I don't see any outliers, but you could have outliers, right? You could have something down here, something over here, any place, an outlier. And it would just mean it looks unusual compared to the rest of all the data points, right? Okay, that's what we're kind of looking at. So in this one, if we were looking at an R, maybe an R value here would be like a negative 0.89 R value. I'm just saying for an example. I don't know. I don't have actual data in front of me. I'm not plugging stuff in. I'm just saying for an example. And what you would say is this is a strong because it's between -1 and negative 0.8. Negative linear relationship. And of course, when you're talking about this and you're writing this up for me, you're always going to talk about the context of the problem. You're always going to discuss the context with it. So if you're looking at height and weight, you would say, oh, there's a strong negative linear relationship between height and weight, just that kind of thing. So it's still like the same statement. It's just you're adding the context to it, adding some meat to the problem.